Okay, so I may get this example done in the 11:15 class, but for the 9:05 class, where I said I wanted to do this one, we didn't quite have time, and I would post a video of it. We're going to solve this problem here, where I've set up a parallel combination of an inductor, a capacitor, and a resistor. And as you can see, I have carefully chosen some values so that hopefully we get some nice numbers at the end. I didn't fully check how nice this initial condition is going to be, but it should be solid. 9 milliamperes, 1/9 kilo ohm is 1 volt. So this should have some nice numbers. I picked a moderate amount here. And I checked the various energies, and so it should all check out. Okay, so or calculate the energy in my head, so it should be fine. So we're going to find VC of t for t greater than 0, and this is the style of question that I usually like to ask on the test, and there's also a homework question in this style, so I kind of picked these values so that I could pick some nice moderate kilo ohms, microfarads, henries. The inductor's kind of big, on the order of 1's kind of large, but I give up on trying to get the numbers to be too nice, while at the same time picking realistic values. So at any rate, what we have to do is set up the differential equation on this. And so in a problem like this, we're given the initial conditions and we don't see the source that was here before that set up this situation, but you can kind of assume that what happened was there was a source network somewhere, and then some switches moved and now it's gone. And that's the way we think about these questions. So it doesn't matter exactly what the source looked like that set up these initial conditions, it just set them up and we've got to go from there. So this is the picture for t greater than 0, and we have our initial conditions and we just see what's the form of this voltage and what is its value. So we need to set up a differential equation here, and to do that, since this is a single node pair, we're going to put ground here. And that makes VC of t act as a node voltage if I do that. And then we can write KCL in terms of that voltage. So there are no sources, so I'm just going to say 0 amperes is equal to the sum of the currents here, here, and here. Make sure I'm recording. Yes, good. I can see the audio too. All right, so we need to write the 3 currents that are involved. And just like with the example that we left off on today, Friday, we're going to have 2 versions of this equation. And one of them, well, we'll get to that in a second. In either version, let's actually write them both at the same time, we're going to express the resistor's current as VC of t over 1/9 of a kilo ohm. And we get the same thing here, VC of t. There's only going to be one difference in the 2 things that I write, but it's going to pay off momentarily. Then we have the current in the capacitor, which is C dV dt. So this is going to be 10 microfarads times VC prime of t. And then we'll write VC prime of t down here again. And then the last thing, this is where our 2 versions are going to differ. In one of them, we're just going to write this as IL of t. This is going to be our initial conditions equation to help us out. And then in this version, we're about to set up the differential equation version. These are the same equation, just written 2 different ways. For the differential equation version, we write IL in terms of VC. And so that's going to be 1 over 5/7 henries times the integral from -infinity to t of VC of tau d tau. All right, so then if I take the derivative through this equation, let's actually save that We'll put a pin in that for now. So let's resolve the initial condition equation here. So we already know from above, the values of VC of 0 and IL of 0. So we're going to get those two things involved. So in the initial condition equation, for t equal to 0, we're going to get 0 amperes is equal to, so we need to plug in VC of 0. So VC of t, we're going to plug in 0. VC of 0 from the given initial conditions is 0 volts divided by 1/9 kilo ohm. Oh, and I should have been putting parentheses around the ohms and henries, otherwise it's kind of confusing when I have fractions in there. But I chose the fractions so that we'd get nice numbers at the end, at least as much as possible. So, okay, so that's our VC of 0. Then we get plus 10 microfarads, VC prime of 0. Plus IL of t. So IL from our initial conditions above was 9 milliamperes. So that's 0 volts, 9 MA. I was just dropping that information in here. So that goes to 0. And so then we get that VC prime of 0 is then equal to negative 9 MA over 10 microfarads. So that's negative 0.9 milli over micro is kilo. Which is fine. Yeah, the derivative is going to be pretty large because of the, yeah, okay. So 0.9 kilo, an ampere per farad. Farads are seconds per ohm, and then it's amperes over seconds per ohm. So amperes, the ohms are going to come up top. And so then this is equal to minus 0.9 kilovolts per second, which is fine, and is thus negative 900 volts per second, which is absolutely a reasonable derivative in this case, especially because I know what some of these numbers are going to hand me. 900 was a number when I was writing the problem. So, okay. So everything looks like it's going pretty well. So we've got our VC prime of 0, and the fact that VC of 0 was 0 volts in the first place. We resolved our initial conditions, so that's great. Then we still need to deal with the differential equations part of this. So I'm going to take the derivative of this equation here. And so we're going to get 0 amperes per second, time derivative, started with amperes. So 0 amperes per second is VC prime of t over 1/9 of a kilo ohm plus 10 microfarads VC double prime of t plus 1 over 5/7 henries VC of t. We'll rearrange the terms. We'll divide the 10 microfarads over. Okay, so 0 amperes per second over 10 microfarads equals VC double prime of t plus 1 over 1/9 kilo ohms So we'll just do 10 ninths kilo ohms times microfarads, because I'm just dividing the 10 microfarads down here. VC prime of T plus, okay, we're dividing this down here. This is going to be 1 over 50 over 7. And then our units are going to be microfarad henries. And as long as everything has worked out, our units are going to be okay. So amperes per second, microfarads. So again, a farad is a second per ohm, and a henry is an ohm second. So if we resolve all of our units, amperes per second, the micro doesn't matter because it's going to get a 0 on it. So we're just talking amperes second, or amperes per second farad. Farads are seconds per ohm. So then the ohms are going to come to the top, and we're going to get volts per second squared over here, which is good because VC double prime of T has exactly those units. 10 ninths, so a kilo ohm times a microfarad is a millisecond. So if we flip this over, this is going to be 0.9. So kilo ohms times microfarads is milliseconds. So this is going to be milliseconds to the -1 VC prime of T. And if we multiply microfarads times henries, this is going to be 7 over 50. So we could actually write that then as 0.14. Oh, sorry, I forgot the VC of T over here. So then this is microfarad henries. So farad henries are seconds squared. So the micro is micro square seconds. Okay, so this is micro. If we write it as seconds squared to the -1. So the overall is micro and we get square seconds. So the micro, because the seconds are squared, distributes across them, milli and milli. So if I go to clean up my units, and actually I ran out of paper, 1 second. If I go to clean up my units very carefully, this is going to be 0 volts per second squared equals VC double prime of T. And the units are where this kind of gets ugly. So if we the milli was in the denominator. So when it comes to the numerator, we're going to get kilo. So milliseconds to the -1 is kilohertz. So this is plus 0.9 k hertz. If we don't want to write seconds to the -1. And then this is plus 0, or wait, so then it's VC prime of T, and then 0.14. So microseconds to the -1 is actually going to be kilohertz squared. Micro square seconds to the -1, kilohertz squared. Kind of a pain. It's a 10 to the 6, needs to come to the numerator. if you can kind of keep track of it your own way, but ultimately what ends up being the case is that 0 is equal to VC double prime of T. So this kilo is going to give us 900 VC prime of T. And then this is going to be 14, 1, 2, 3, 4, 5, 6 places over. So this is going to be VC of T. If you resolve all of the millis and micros up front, you can, it's probably easier than keeping track of my weird version of it. So it was probably wiser at this moment right here. Let me redo that real quick. So it was probably wiser to just say, okay, kilo times micro. So we can just say 0 equals VC double prime of T. So this is going to equal 9/10. Kilo times micro is milli. In the denominator is 10 to the third, because this is times 10 to the third times 10 to the minus sixth. So 10 to the minus third in the denominator, 10 to the third on top. Oops, that's plus VC prime of T plus. Down here, there's a micro. So this is going to be 7/50 times 10 to the 6th power VC of T, which leads to these calculations right here. Okay, so anyway, we end up here. If we declare VC in volts, time in seconds, the equation looks like this. If we declare time in milliseconds, then this starts to look a little bit different. So if we declared time in milliseconds, our differential equation would look like this, 0.9, 0.14, if time is in milliseconds. But kind of up to you along the way. So here I'm just letting time be in seconds, and then everything's kind of nice. Okay, so we end up with VC double prime plus 900 VC prime plus 1400 VC. Hey, look at that. 14 has factors of 2 and 7 as prime factors. 2 plus 7 is 9. And then I've got 00, 00, 00. So if we throw this into the quadratic formula or factor it, it's not going to matter. The characteristic equation tells us that 0 is equal to s squared plus 900s plus 140,000. And so on a test where I didn't want to create, where I don't care about creating realistic values, I'll pick ones that aren't so annoying to keep track of. But for this problem, I wanted to make it a little bit messy at least, while still being nice numbers ultimately, but a little bit tricky to track the units and make sure everything checks out. Okay. And so this is the time in seconds version. So the alternate version, if you write it as, so that's the time in seconds. Side note that if time is measured in milliseconds, of course, this pen is going to die at this moment. Let's try this one. If you measure time in milliseconds, then you'll just get s squared plus 0.9 plus s plus 0.14. Everything else about the calculation will be the same. So if your time is in milliseconds, you get this equation, and then a bunch of other stuff happens. But okay. All right, so this is the time in seconds version. So if we throw this into the quadratic formula or factor it, it doesn't really matter. This is going to be negative 900 plus or minus the square root of b squared, which is 81, 800, 10,000 minus 4ac, so 4 times 14 is 16 plus 40 is 64. What? 56, right? 56. That makes sense to me. So then the result is going to be yeah, 56 over 2. See, it would have just been easier to factor it. And so then this becomes negative 900 plus or minus. This is the square root of 25,0,0,0,0, which is pretty much exactly what I wanted. This is s equals. And so then the square root of this is negative 900 plus or minus. The square root of this is 500 over 2. And so our two solutions for s are going to be negative 200 and negative 700. Oops, negative 200, negative 700. So this is what we would call an overdamped condition. So we have two distinct real roots. And from here, we have our initial condition and this. Pause for a sec. Okay, resuming the recording. So we have our initial conditions and our two real roots. So we know that the VC we were interested in as a function of t has the form a1 e to the minus 200 t plus a2 e to the minus 700 t. And thus, VC prime of t has the form negative 200 a1 e to the minus 200 t plus negative 700 a2 e to the minus 700 t. Like I said, 900, pretty reasonable number. And so, or there's the negative 900. Volts per second is a reasonable number here because my time constant gives me hundreds already. So I intentionally chose this. So that sure enough, this has what I would expect. Yeah. I think I mentioned already that the secret to making sure it would work was just to look at the resistor's value, choose a current that the voltage across that resistor would have to be a reasonable number of volts. I chose 1. And so sure enough, all of our numbers tend to work. Okay. So we end up with these two things. And so we just have a system of equations to solve. So if we plug in 0 into these formulas, we'll get that VC of 0 is 0 and must be equal to A1 plus A2. So that's fine. And then VC prime, which we know to be negative 900, is equal to negative 200 A1 plus negative 700 A2. Okay, so not a terrible system of equations at all. So we'll take 200 times the first equation and add it to the second. So as a result, negative 900 . Okay, so I cancel the A1 by adding 200 of the top equation. Since this is 0, it doesn't change the left-hand side. So adding 200 of this takes us to negative 500 A2. And therefore, A2 is just equal to 9/5. And then plugging that back into our first equation, A1 is equal to negative 9/5. Therefore, the form of our solution and the exact final calculation is that VC of t is equal to negative 9/5 e to the minus 200 t plus 9/5 e to the minus 700 t. So our time constants, or the decay times here, are 0.5, or sorry, they're like 5 milliseconds and whatever this is. So the faster decaying one is this one. This is the answer. I just have a couple notes at the end about what this tells us about our solution. So the one here, so this one, for a given amount of time, this one decays much quicker. So our initial capacitor voltage is 0. We know that V prime was, where'd it go? We know that V prime was negative 900. So we know that our capacitor voltage is decreasing from 0. And that's true in the form of our solution. This decays faster. So for all time, this exponential has a higher magnitude and it is negative. So the voltage starts at 0, goes negative, and then because it is overdamped, it goes, it kind of makes a move like the voltage is going to go. It starts at 0 and it's just going to go down and then decay back. And I'm not sure where it peaks. You can take the derivative of this and set it equal to 0 to find the minimum location. Whatever you want to do, but it looks something like this. I don't know how large it is. You can find the minimum, plug it in, and see what the value is. But it's going to be less than a volt. I'm fairly confident if I remember the solution forms and the trick that I mentioned, that the voltage on the resistor using the initial inductor current would be 1 volt. So the VC shouldn't go lower than negative 1 volt, I don't think, at the peak minimum value, because the resistor is always going to be sapping power. And so then it's not going to reach the full 1 volt that would be necessary to make it work out. So it'll have a peak somewhere. That peak will be negative probably like 0.6 volts or something, but you can calculate that out if you want. So that's that example. This is the type of question that I like to ask on the test. So I'll end the recording, post this on the YouTube, and you can watch it later and get good prep for the second order question on the test, on the final. So have a good day, everybody. Bye-bye.